Okay, hi everybody. So it's time to continue. Okay, okay. Hi everybody. Hi. Okay, so we are going to start. Okay, perfect. Okay, so we have another session, the after lunch session. Okay, and then we have another one, which is the evening session. Okay, but okay, we're now going to the after lunch session. Perfect. So let me give you a kind of high level overview. So the question is, during the before lunch session, we have introduced you to the concept of variational inference. Our problem is always to compute the Bayesian posterior. We can't in many relevant cases, and then we have to resort to approximate inference method. In this case, we are studying variational inference method, and then we saw how to solve variational inference method, how to approximate an approximation of the Bayesian posterior in a nice and scalable way. But the question is that so far, as you have seen, we have been dealing with linear regression models, Bayesian linear regression models. Why? Because the kind of techniques that we have covered before lunch only applies to what is called formally conjugate exponential family models, where Bayesian linear regression is one example, but there are a lot of probabilistic models that fall within this model class. Okay, so when your model belongs to this nice model class, then you can apply this standard variational inference method, then everything is going to run very smoothly and very nice. The question is, like, not all the probabilistic models that we may be interested in really belongs to this nice but constrained model class. For example, I'm going to introduce you to this kind of more general model class, something which can be called, is called in the literature like Bayesian neural networks, okay? So what's the idea of that? The idea is, imagine that instead of having, this kind of linear regression problem where, there is a kind of linear dependency between your X variable and your Y variable. Now, I think it's not really hard to see that this linear approximation would be a very bad idea. No? Okay. So it's much better to use something which is not linear. Okay. Perfect. Some non-linear model. So one possibility would be to go for a neural network. Okay. Neural network, they are fantastic function approximations method, which, if you train a neural network like something like that, okay, with some hidden layer up here, okay, and then you can learn it using PyTorch, okay, you define your loss function, that in that case will be the mean square error, okay, and then you run it, then you minimize, and then you learn neural network. In this case is a multi-layer perceptron with one hidden layer. And this multi-layer perceptron is quite nicely able to somehow, okay, fit this kind of sinusoidal, non-linear relationship between the X and the Y variable. Perfect? Okay. But you know the story now, no? Which is the story? The story now is that this is one solution. Perfect? Probably it's the most probable, it's the most possible solution, yes? But this is one solution. And Arto mentioned at the beginning of the school, and we have been telling you once and many times, it's not a good idea to consider only one solution. So we want to consider all possible solutions. And then for doing that, what we can do, Bayesian, okay? We can do a Bayesian approach, perfect? So we go to Pyro, and then instead of considering the parameters of my multilayer perceptron as a single parameter, we treat the parameters of the multilayer perceptron as random variables, okay? Using Pyro. Perfect. Okay, I'm not going to go through the details. And the question is, I apply variational inference, okay? I optimize my elbow, okay? And what I get is this result. So let me show you a bit. So the question here is like, there are, I think it's what, 1,000 lines, which means like 1,000 multi-layer perceptrons models, okay? So, and then each line is one of these multi-layer perceptron models, which has been sampled for the variational posterior. Okay, so each line over here, there are 1,000, represents one of the 1,000 possible solutions for this regression problem. And by doing this, what we get is that we capture uncertainty. Okay, we capture we approximate all the possible multiple solutions. We approximate all the possible multiple solutions. The question is, in order to do that, did we apply what we learned before lunch? No, unfortunately not. Okay, why? Because these kind of nonlinear models, they don't belong to this conjugate exponential family class. I mean, you cannot derive this kind of closed form updating equations, and then we have to do something else. But the nice thing and the positive news is like, we can do something else, okay, with this kind of much more complex, much more expressible, okay, probabilistic models, okay? And this is what we are going to learn during this after lunch session, okay?
Okay, so when I start talking, you know that now we're going to do slides again and theory and stuff. And that's true also after lunch. I'll start quickly with stochastic gradient descent. And I know that you know, but I'm going to say it anyway. First thing is, why do we even talk about that? Well, we are going to try to optimize the elbow using gradient descent. And that's kind of nice, because when we are able to do that, we can outsource the elbow optimization to a solver like you find in PyTorch. So we can integrate with other things from PyTorch into our probabilistic model, just like Andrés showed you on that slide. So to get there, I'm first going to say something about gradient descent and stochastic gradient descent, and then we will look at the gradient of the elbow afterwards. So gradient descent, we have this function f that we would like to optimize. I'm going to maximize that guy. It's a parameter, or it's a function of the parameters lambda. So what do I do? Well, I'm starting with random initialization, and I'm just updating. So for every step, make a small move in the direction of the gradient. Sooner or later, this is going to converge if f is nice, and if rho is sufficiently small. And I'm skipping the mathematical details here, so this is well known. And here we have an example of that at work. So now f is here the log likelihood of 1,000 Gaussians that I have sampled. My parameters are the mean and the precision, so 1 divided by the variance. So I have the mean here, and I have the precision up there, and I am gradient ascending, starting from some random position up there, and then moving slowly but directly towards the optimum. So this works well. So far, so good, but that is not going to help us all the way towards solving this elbow optimization. And the reason for that is that we will not be able to calculate the gradient of the elbow exactly. So there are two things at least that is going to make it a little bit harder. The first one is we won't be able to work on the full data set at all times. So we will do subsampling, mini batching, and thereby introducing some randomness into the process. So each subsample can be seen as a random choice out of the full data set. and therefore there is some stochasticity there. And secondly, we won't be able to calculate the gradient exactly, even if we are looking at a smaller sample. So there will be some problems there too, but we will fix that. Anyway, we won't be able to do gradient descent. We will use stochastic gradient descent. And again, as you know, I'm quite sure, if we have an unbiased estimate for the gradient, meaning a function g in this case, that guy over there, this is a random variable with expectation equal to the gradient at the point lambda, and with a finite variance, then things are going to work out for us anyway. And then the requirement is that this learning rate that was a constant previously is now a sequence of numbers that is slowly going towards 0. And by slowly, we mean that it obeys these Robbins-Monroe sequence criteria. So all of that you have seen before. I just mentioned it now anyway, because it's going to be crucial for us when we are trying to optimize this elbow through gradient descent. Oh, and I have an example too. So here is the example again with our 1,000 examples from the Gaussian. And the key point here now is that when we previously had this very smooth trajectory towards the optimum, now we have a more like a random walk behavior, still getting to where we want to be in the end, and then not really converging, but moving around where the best parameters are. So there is some stochasticity also in the behavior of the solution path. And then we can move on to the black box variational inference, as it's called, which is now then optimizing elbow based on gradients. So again, the main idea here is to be able to maximize the elbow, not using the coordinate descent and the pencil pushing approach that we did before lunch, but rather to use standard tools that we get right out of the box with Pyro or PyTorch or TensorFlow probability or whatever. So we are going to then try to find this gradient of the elbow. If we can do that, then we know what to do. Oh, again, the algorithm is straightforward. Initialize, have some learning rate sequence, just go, done. So the important issue is, what is that? How can we calculate the gradient of the elbow with respect to the parameterization of our Q function efficiently? So that's what we are going to look into. And that's semi-tricky. So there are some semi-tricky slides coming up next, but you've just had a big break, so I'm sure you can manage. On top there, I'm just writing out what the elbow is. So we're looking for the gradient of this guy with respect to the parameterization of Q, which is then exactly what this is, because that's the elbow. The tricky thing now is the parameterization here is what we are taking the gradient with respect to. So we can't really move the gradient inside the expectation without at least making some adaptations. And these adaptations are kind of pencil pushing things in nature, so I'm not going to go through them. I'll just mention that there are 3 things that we need to get there. First one is the rule of a product. The gradient of a product is straightforward as it is for ordinary derivatives. The second one there is kind of clever. This is called the log trick. And it says that the gradient of a function f is the same as that function times the gradient of the log of that function, which is going to be useful. And then we have this relationship here. The gradient, the expectation of the gradient of some density function with respect to its parameters are always 0. This is, again, more pencil pushing than really informative, so I'm not going to go through that. But the key point is we started with this one where we had the gradient outside the expectation, and we end up with this one where we now have the gradient inside the expectation. And that's going to be helpful. So let's look at this equation and see why it is possible to compute it. So that's what we want to go. We want to be able to calculate this thing here. First up, it's nice that we still have here the joint, not the posterior, so we can calculate that, the thick part. Secondly, for the yellow part, we can still assume mean field and all that, so this one here should be possible to calculate efficiently as well. When we move to the green part, this is something that's called the score function gradient. And basically, if we assume some kind of distributional function for this Q function here, like a Gaussian or whatever, we can calculate this derivative by ourselves. If we are using some kind of, say, neural network to represent this distribution, we can also then rely on autodiff or whatever to find these gradients. But these gradients, they need to be found, and you guys will get to try that actually quite soon. And then for the last part, the expectation, what we're going to do is just to sample. So the expectation over theta coming from the distribution Q of whatever is, of course, just infinitely many samples of thetas from that Q distribution and evaluated, then taking the average. So we can numerically approximate this guy. And why is that enough? Well, it's enough because we don't have to have the exact gradient. We have to have something that is in expectation the corrected gradient. And this sampling scheme is going to give us that. So typically, generating those samples is going to take many samples if you want to have the gradient exactly. But what we need is to make sure that the gradient has a variance that is finite, and basically that's it. So in applications, you typically see, say, 10 max samples for evaluating this expectation. Okay, so in summary, we are going to calculate this thing here inside the square brackets. That's doable. And then we are going to evaluate that at sample points that we get from this distribution, and then take the average, and that's how we calculate the gradient of the elbow. So not really computationally difficult. And here is a plot that I have stolen from Arto, who had this talk last year at ProbAI. At least I've stolen the design. So what is happening here now is that the blue thing here is our true distribution, the one that we try to approximate. The green one is our current variational approximation. And then these different links, they are building up to become the elbow gradient in this parameter space. So if you look at this black dot here, for instance, this is one of my M samples. Okay? So what happens here now is that we see this red arrow. That is the score function gradient. So that's this guy. So what this gradient is telling us is how would you need to change Q in order to make that data point more probable. So that means always move the center of mass here towards data point. So this gradient here is pointing directly away from the center here. So that's the red one. Then we multiply that by this part. So what that means again is, say this one here is more or less constant over our sampling space, then is the log of 1 divided, or a constant divided by the probability of that point with respect to the generating distribution that gave it to us. That's going to be really, really large if the sample is of low probability from Q. So that's why this guy is long. And it's going to be smaller when we are making a more probable sample. So this guy here is shorter. Okay? And then why is it pointing in the different direction? Well, it's because we are taking the probability of P divided by the probability of Q in that data point. And the sample is from Q, right? Whereas P is somewhere in the distance that we're trying to get. So typically, P is smaller than Q, meaning that this thing here is going to be negative. And that's why we then have to swap the direction of the link of the arrow from the red one to the black one. And this I'm doing now for m times. Here, m equals 5. And taking the average gives me this green arrow, which is then where we are going to move after these 5 samples have been generated. So this is my approximation of the gradient of the elbow using these 5 samples. Does that make sense? It makes sense. The problem here is, as I alluded to, that these guys that are less probable, they have the largest influence. So if I'm unlucky and get something, say, down here, then my gradient is going to be like up there somewhere. If I'm having only a few samples and one of them is a low probability one, then that might really throw my search off the scent and go away in a different direction than it should. And this is because I am trying to approximate my expectation through these samples. So, yes? So this is not, these are not real examples. These are my invented samples for trying to evaluate this expectation. So I'm generating new random samples from Q just to be able to calculate this expectation. So they don't really relate to the data, they relate to my sampling. Other questions? What would happen if the gradients are? Yes, so in expectation, the gradient has to be correct. And since this is a Monte Carlo sampling instead of an expectation thingy, then we know that Monte Carlo sampling is an expectation correct of whatever function they are sampling from. So we are safe. So I'm trying to make this argument that this here in my stochastic gradient thing in intro, then this thing here would be the gradient of f. But when I'm not able to calculate this expectation, but sampling instead, then what I'm doing is to approximate that by a random variable, which in expectation is correct. So the stochastic gradient descent machinery is working here. So here I'm only using the mean field assumption for efficiently evaluating that thing. I could have also done it otherwise. So what I'm going to get then is that this lambda vector is going to be much larger if it, say, contains upper triangular matrix for the covariance instead of just a diagonal. So that means I have more stuff to do, but it is working also without the mean field here. But the mean field is going to help me for that one and for making this one smaller. Yeah, easier. Yeah. Other things? Yep. So we had this meeting before when I suggested that we should use this slide, and then Thomas, I think it was, asked exactly, why do we call this the spore function again? And no one could answer. So, and I even Googled it, but I didn't find it because it was so much noise in the Google return. So I don't really know. Yes. So there is, and we need to be able to sample from it. So there is a summary slide at the end that you are already at. I'm not. Good, you're the clever one. More questions? I guess if you are sure that it's correct in expectation, you could do that. There was someone at the back too. Yes. Yeah, so these I's, they should have been J's according to what we did previously. I just realized that when I was waiting. So these are the dimensions of Q. So this is the kind of mean field thingy. Sorry. Yeah. Yeah. More questions? You guys are the few selected out of the 800 applicants. So I know that if someone here is wondering about something, then it's because it's not clear. Yeah. So you mean by attacking this property here? So going here? Is that what you would like to do? Yeah. Okay, good. More? No. Okay, so as I was saying, the least probable samples are the ones that will influence my estimator the most. And here I have a number of different representations of 5 samples in each picture. And then we can see the variation. So this guy is pointing up there. That one is longer and pointing that direction. This one is small and going completely wrong. And this guy here is actually the one that is doing the best. But that's based on 2 very improbable samples that somehow add up to become something that's nice. So this approach has the problem that the variation of the gradient is large, and that makes training here fairly unstable. And that is, of course, then only for 5 samples. So here I have more samples and less samples. So here I have 3. Lucky with those samples, direction is good. 5, 10, and 25. And the 25 one is very good. So the more samples you make, the better your gradient approximation is going to be. But of course, also the more compute you will have to spend on each step in your optimization routine. So then finally, video. Here, if you remember the Kavi video we had before lunch and compare that to what's happening now, you can see that this one is like going in the right direction all the time, but it's kind of swimming around and doesn't really stop. So it's kind of swimming on top there until the bitter end. I just stopped making pictures. So this thing is a floating thing, also just like you saw from the update of the maximum likelihood estimator based on mini batching. Yep. And then you will destroy the correctness of the expectation of the gradient estimator. So you'll have to live with this. There are ways of trying to fix that. Some control variables, for instance, and the reparameterization that we will talk about next. So there are tricks. This is just like the first step towards the reparameterization, which is the one I guess we would recommend to use whenever possible. Good. Yep. Well, I would say that desperately depends on how your posterior actually look. So if you have strong correlation in your posterior and you fail to get that through to your variational approximation, then it's going to have problems with actually exposing the uncertainty that you have in your posterior. And then for sure, mean field is going to be helpful. So there are good use cases for relaxing the mean field assumptions when you can. Good. Now we have this workbook that we have prepared for you. So now the task is for one's linear regression. And we have the same model as before. So we have these two unknown parameters, W0, W1. We assume that there is linear relationship and all that. So what we would like you to do now is basically just to dive deeply into this and show or try to find these gradients. And in the workbook that I'll show you next, we have given code for approximating the expectation, for calculating these things here. So your task is to find this guy. We have implemented that for the sigma parameter, but you are supposed to do it for the mu parameter. So basically, you need to calculate the partial derivative of log q with respect to mu, implement that into the workbook and a notebook and see how it runs. And I'll show you the notebook too. Okay, so we start on the top by just setting up stuff. This should run without much trouble, so I don't think I'll go into the code here. Then we have prepared code for you to calculate p and log p, log q, and the elbow. And then there is lots of stuff going on for being able to make these nice samples that we learned from Aito with the PDFs and the gradients shown as arrows and all that. So again, not something you need to look into. And then we have something called compute gradients that is basically running the show. So sampling several times and averaging and all that. So that means we are jumping straight into the definition here of the score function gradient. And that's where you will do your stuff. So here, some theory summarizing what happened in the slides. And then we are asking you to compute the gradient of log q given here with respect to mu. We already have it with respect to sigma, and that's written down here. So you can then try both and see that you get the same result as we did for the sigma. One thing to notice here is that we are using a little bit of a funky data structure. So this is something called parameters. It's like name tuples, but they are mutable. So what that means is that you are supposed to fill in something here for the keyword mean. It's supposed to be an NumPy vector of size 2, where the first one is for the offset, the second one is for the slope. And as soon as you've done that, this here is finalized. And then we return the gradient, which is the score function times this weight, which is the log p divided by q. Packaging for plotting, and you're done. And then this one here is the one that you run to check your solution. That will generate plots showing the convergence of your gradient-based elbow optimization towards the true posterior in the regression example. So the link is same as always, student black box variational inference this time. And how many minutes did we have, Thomas? 20 minutes for this. That should be more than sufficient, I think. So just play around with it, and then you can also look at what happens when you change the number of samples per iteration, for instance, just to get a feel for the robustness of this.
just to be sure that you understood the exercise. Okay, yes, let me. I mean, yeah, yes, let me, yes. So here you have log Q, okay? You have the density of the log Q. Here you have how we computed the gradient with respect to sigma, okay? You just convince yourself, okay? And then you go down here and then convince yourself how we coded this gradient here. Perfect, okay? And then you have to do exactly the same for mu. You compute it manually, and then you go and introduce the code. No. The only parameter, exactly. So the only thing, the only place where they have to, so here they have a vector of 0, 0 vector, okay? So what they have to do is to do exactly the same like here. So it's like some piece of code that will return two numbers, okay? That means the gradient with respect to mu for the first variational parameters and the gradient with respect to mu for the second variational parameters. Exactly as we did here, the gradient with respect to sigma for the first variational parameter and the gradient with respect to sigma for the second variational parameter. Perfect. So you just introduce that here. Okay, you just create an empty array, you know, and then, I mean, you can maybe just even copy paste this piece of code and then changing the code for computing the gradients, okay? But before that, convince yourself of this gradient that we have already provided you and then go for the mu. Perfect. I think it should be doable.
So what do you say, guys? Are we ready to see the solution? We see the solution. So this shouldn't have been too hard. It's camouflaged into lots of math, but the actual thing that you were supposed to do is not that complicated. So what we are going to do is to start off from the log of Q and then take the partial derivative with respect to mu. So that means nothing comes out of the log 2 pi thing, nothing comes out of the log sigma thing, and for the last part you'll get 2 times theta I minus mu I divided by minus 2 sigma squared times minus 1 again, right? This is just a partial derivative of the last term here with respect to mu I. So kind of straightforward, and it's written up down there. So then what we have to do is to put that into the solution thingy down there. And that's basically all that you needed to do to get this to work. For the sigma part, I should mention that the solution here is implemented slightly differently from the actual equation that we gave you on top, which was kind of a bad thing to do, but they are identical. So I hope you didn't get confused by that. But you were supposed then to do this, and that was not hard, I hope. And then having done that, you could run the test thing and see the results. Starting all the way from the top here, or almost at least. So going down, we see that we are approaching the correct distribution slowly but surely. And then moving a little bit around, but eventually getting there. And every now and then we get these kind of warnings. And what that means is that there is a test in the move of the optimizer, so that if the optimizer wants to move to a negative sigma value, which is not meaningful, then that just means that this step is not taken. So if we have a really bad gradient estimate, then we are kind of using this as a safety blanket to get away from that problem. Yeah, just disregarding those gradients that would lead us to negative variances or negative standard deviations. So that's why you get these warnings. No harm done, as it says, so just keep on going, but then disregard that movement. And the more unstable your approach is, say you go with m equals 2 instead of m equals 5, as we have here, the more of these warnings you typically see. So this is a problem with the score function-based gradient. And then during the break, I also got to learn why it's called the score function. So that was due to Sir Fisher, one of the, say, classical statistical guys. And I was also told that he called it a score function because he used log of the PDF. And when you evaluate that, it can't tell you the probability, but you can still use it to score something. So say that this is more probable than that. I don't know what the actual probability is, but I can still rank them. So therefore, score function. Anyway, this here ends up in a decent spot. And that's actually what we wanted to see. So this is our first endeavor into gradient-based elbow optimization. And now we are actually going to give you a break for 5-10 minutes. And then after the break, we will see more advanced methods of gradient optimization that are not as volatile as this approach is.
Okay, so yeah, we are going to continue. Okay, so let's continue. Okay. So well, so far, you know, okay, sorry, yeah. Sorry, say again, say again. Exactly. I think yes. Exactly. So the problem is, as Helge pointed out before, is like, you know, so one of the parameters that we want to optimize, we have to optimize the mean and the variance, okay? And then the variance should be always positive. It's a constraint, okay? So when you are in some position and then you move along the gradient, okay, if the gradient is not well computed, you know, you may just end up in the wrong place, in a negative value. And then we go back, okay? And this is what happened, you know, when you have this, when the gradient is not, I mean, it's a Monte Carlo estimation. And if the Monte Carlo estimation is not very accurate, there's large variance, this kind of things happens much more usually. If you increase the number of samples, the M, okay, if you increase M, you will have higher quality Monte Carlo estimation, and then this, you know, moving beyond what you should, okay, is going to happen less often. Okay, perfect. So the question is that this is a, I mean, this is a pretty general technique. Actually, it's quite powerful. Okay, but the problem is that, you know, as Helge said before, the kind of quality of the gradient estimation that you get is not good enough. Okay, you have large variance. Sometimes your gradients, okay, can vary a lot. Okay, and the problem is, the question, like, there are some techniques that build on top of that, which are control variates techniques that try to reduce the variance. Okay, and then you have something better. But the problem is, like, when you start to increase the size of your model, the number of parameters of your model becomes large. And here we are talking about that we really want to go in really large probabilistic models, okay? Something like 1,000, you know, we're talking about deep neural networks in size. So we're talking about really large probabilistic models. I mean, when you increase the size of your probabilistic model, there is no way really to control the variance in this case. And I mean, it's kind of, doesn't really work in many settings, okay? But fortunately, we have a different trick, okay? So what we're going to tell you now, I'm going to tell you now is a different approach to compute the gradient of the elbow, So at the end, what we have to do is optimize the elbow. And in the settings, we want to compute the gradient of the elbow, making minimal assumptions, okay? And as we discussed before, the problem of the gradient of the elbow is like we have the gradient of an expectation where this expectation, this Q, depends of lambda, and you cannot really move the gradient inside. Perfect. So what we're going to do now is we are going to make this assumption. Perfect. So we are going to assume that the kind of variational approximation, the variational approximation family that we use is reparameterizable. What does it mean? It means like this Q, okay, when I want to sample from this Q, I can do it in this other alternative way. I can sample from this Q, okay, by firstly sample some distribution over some epsilon. And the key point here is this distribution over epsilon does not depend on the variational parameter, okay? It's a distribution over epsilon which doesn't depend on the variational parameter. Then I will sample this epsilon. And then I will find, I assume that I have a function that once I take this epsilon as an input and the lambda, this deterministic function give me back, okay? Perfect. One example, the Gaussian distribution. The Gaussian distribution can be generated, you can generate Gaussians, normally distributed samples by sampling by a 0-1 normal distribution, okay, which doesn't depend of the variational parameters, which for the normal distribution would be a mean and a variance, and a standard deviation. So if I sample from this distribution, which doesn't depend on the variational parameters, and then I sample some epsilon, then I take epsilon times sigma plus mean, then I got this theta, whose distribution is really a normal distribution. Perfect. That's a standard properties of the normal distribution. But the nice thing is I'm able to express this Q in that way. First, I sample from something that doesn't depend on the variational parameters, then I transform this epsilon through a deterministic function that does depend on the variational parameters, and then I get my theta. So what's the nice thing? The nice thing is like, once I have that, I can start to, make some mathematical tricks. Then we will go through them. The first one is, I can change. So if I have before this expectation over theta, I can transform this expectation over theta of this part over here. Okay, this part is the elbow. Okay, and then gradient of the elbow. So I can take this expectation and I can replace the sample with respect to the variational with the sample with respect to this phi distribution over epsilon. Perfect. And then once I have the epsilon, I replace the thetas by this deterministic function that depends on epsilon and the variational parameters. Perfect. And then this is equal to this part. Nice. Which is the key point here? The key point here is now this expectation depends on a density phi, which does not depend on the variational parameters. This phi density does not depend on the variational parameters. The dependency with respect to the variational parameters lambda is only through the deterministic function f, which is now here inside. And outside here, there is no any lambda. Okay? So the nice thing is I can take this gradient with respect to lambda and move it inside. Okay? And now I have something which is quite nice, which is the expectation with respect to gradient. Okay? So I can proceed further and then I can apply, I can derive, I can take this derivative, this gradient with respect to lambda, and then, applying the chain rule, then I have that derivative with respect to lambda of this guy equals, the gradient with respect to theta of this guy with respect to theta, okay? Times the gradient with respect to lambda of this deterministic function plus this term over here, okay? First thing is like the expectation over this term, Helge pointed out before, is equal to 0. So can be discarded. And then we end up having this expression over here. Perfect. So which is the nice thing that, we have our gradient of the elbow expressed as like the expectation of something, the expectation of some gradients, okay? So this expectation involves a multidimensional integral, okay? But the nice thing is I can apply Monte Carlo estimation, okay? And then I can get an unbiased estimate of this expectation, of the gradient. Biased estimation of this expectation, which is the gradient. Then taking this unbiased estimation, okay, taking this Monte Carlo approximation, I get an unbiased estimate of the gradient. What I do is like I sample a bunch of epsilons. For each sample epsilon, I compute through this F function, which is parameterized by lambda, the theta j, and then, I have the theta j inside. Perfect. I think that's a simple trick. But this simple trick, okay, has very relevant consequences. Okay, if you remember the score gradient function, the score gradient estimator, we computed the gradient with respect to log Q, the gradient of the variational solution. Perfect. That was the kind of gradient information that was given to the optimizer method, the gradient of log Q. But now we have the gradient of log Q, but with respect to theta. But more important is like we have the gradient of log P. Perfect. So we really take information. We have information for the gradient of the model. Okay. And you know what is pointing the gradient of log P theta d? Is pointing to the map, to the mode of the Bayesian posterior. Okay. This gradient is pointing to the mode of the true Bayesian posterior. So we know where the mode of the true Bayesian posterior, okay, is, and then we can move in that direction. And that makes, this gradient much more nicer. Why? Because the score function does not include this information, okay? But at the same time, there is always a payoff, okay? The payoff is, that this log P of theta, given this joint, the log of the joint has to be differentiable with respect to theta. Something which didn't happen with the score function. It wasn't a requirement for the score function. But now the requirement is like this guy should be differential. For example, if theta is a categorical variable, we have a problem. Okay? And another restriction is like Q of theta lambda, which means the variational, should be also differentiable. Sorry, I will say here the log. Okay, but it's the same. Okay, should be differentiable, which is like a requirement that was introduced in the score function gradient. But now it should be reparameterizable, which is a strong assumption. But which is the nice thing? The nice thing is like the number of distributions, the number of options that we have to choose our variational approximation from that are reparameterizable are large. And the nice thing is, you have here an example. There is a nice blog post here that you can have a look. And the nice thing, like this, a growing number. People is figuring out ways to take specific densities and find nice ways to express them in a reparameterizable way, like sampling from some distribution which doesn't depend on the variational parameters and then finding some deterministic function that push these samples through some deterministic function that depends on the variational parameters, and then you recover your original sample, okay? So the family of densities that can be reparameterized, expressed in that way, is really growing. There's a very active field of research. So, which means like we can start to choose, gamma, Laplace. There is a bunch of densities that can be expressed in a reparameterized way, and then we can apply this kind of reparameterization trick to compute an unbiased Monte Carlo estimation of the gradients of the elbow, and in consequence, plug that in optimization method and optimize our elbow. Perfect. I recommend you this paper. Okay, so it's a bit old, the survey. Okay, but I think we say it's a nice starting point just to keep track of this. I would say very, very active area of research. Perfect. Any question now? So far? Yeah, sure. Again, when you reuse your I mean, you will. I mean, the question like F can be a neural network, kind of, and you will learn the kind of specific complex function with this kind of neural network structure that can be used in that case. I think it's Thursday. Okay. I mean, for example, for categorical variables, I mean, it's hard. Okay. I would say that the nice thing, I would say like this is like the de facto method that people use to apply this kind of variational inference to large probabilistic models. Okay. And of course, it's a hard requirement, but fortunately, people is figuring out, I mean, how to solve this high requirement for extensive, wide approximation variational families. Okay, so de facto right now is not really becoming so constrained. Okay, yeah. So well, which is the effect of the reparameterization trick? I mean, this is just a kind of simple illustration for the kind of example that you were looking before. Helge showed you. So that was the true posterior. This is the variational approximation. They are the sample gradients that we have. Okay. Perfect. And as you can see, there is a lot of variance in the direction of the gradient. Okay. I mean, you're moving towards your objective, but you know, there's a lot of variance, okay, in the different gradients. Okay. So if you are a bit unlucky, or you are not very lucky with the kind of samples that you generate, the Monte Carlo samples that you generate, you may be pointing in very wrong directions and having this kind of negative variance and so on. Okay. But this is the kind of thing that happens when you use the reparameterization trick. Most of the gradients, now the gradients points towards the mode of the Bayesian posterior, okay? Towards the mode of the Bayesian posterior. So there is much smaller variance in the direction of the gradient. So, I mean, when you take the average of all these gradients, then you really move in the right direction. Perfect. Okay, it's a different technique that use a different trick that, you know, has this payoff that we need to have a reparameterizable variational family, which actually is not really a big constraint, but, you know, it could be the case. And yeah. Exactly. I mean, the workflow here is like you have your model. Perfect. Okay. Then your model will have some hidden quantities, which usually are the parameters of your model. Perfect. Then these hidden quantities are modeled by some random variable. And then you have to choose the distribution of this random variable, like the prior, okay? And then you have to choose the variational family, okay? Which is the distribution of the variational approximation. You have to make these two assumptions, okay? I mean, the prior is a matter of you may have expert knowledge, and then you can fix the prior. But the variational posterior, then you can define the variational approximation family, taking into account different considerations. Okay, the first consideration could be is reparameterizable. Okay, that's nice, but there is also a problem, which is this reparameterizable approximation, this reparameterizable variational family, a good candidate to approximate my posterior, because you should not forget that what you really want is to approximate your Bayesian posterior. This is your final goal, okay? Of course, if your Bayesian posterior can be nicely approximated by a reparameterizable variational family, that's great. If not, there are trade-offs, okay? There are trade-offs. Perfect. This one, yes. There are a bunch of reasons for that, okay? So first one, here, which is really here, I mean, here we have, before that we have the log of the ratio. This is the score gradient, the log of the ratio. But now we have the gradient of the log of the ratio. Okay. That's one of the reasons. Another reason is like usually what happens is like this gradient is going to be dominated by this term, which is always being pointing to the mode. Okay. This is what happens. Perfect. And you also have this term, which is kind of also introduce some stabilization. Okay. I'm pretty sure that you are able to find some specific models in some specific settings where the gradient of this guy can be higher than the gradient of the score function. Okay. But in general, empirically, I mean, the variance of this approach is usually much smaller than the variance of the other approach. And the main reason is like here you have the difference of two gradients, okay, where usually this guy which is dominating. Okay. And before that you have the log of a ratio, which can be, you know, specifically at the beginning. I mean, the log of the ratio, it was like the main term in the score function. You know, at the beginning, the Q is very far away from the P, and then you have this effect of having this guy very small, and then you have a very large weight, and then you. Yeah. Yeah. No. I mean, let me see. It's a kind of different independence. I mean, so when I said before, I mean, this guy, I mean, it's not in the, I mean, like the functional expression of this guy does not depend of the lambda parameter. Okay, perfect. So when you sample from this guy, the sampling process does not depend of the lambda parameter. It's like if I have different lambda, I will always sample the same epsilon. Okay, perfect. So this guy is going to be of the same size as this guy. So if I have a model which has like 1 million parameters, the dimension of this guy is going to be 1 million, and the dimension of the guy is going to be another 1 million. Yes. Well, I mean, and then you have that exactly. I mean, exactly. So there is no restriction here. Perfect. And as we have also shown here, that's they nicely point out, I have here, where is the multivariate? Exactly, here is the multivariate Gaussian. So in the multivariate Gaussian, so I can treat something which is not mean field, okay, and do it in that way. Okay, perfect. I don't know, let's stop there, yes. I mean, if you are careful enough, potentially yes, okay? I mean, if you do some mean field, potentially yes. Because at the end, what you want to have is like the gradient with respect to the variational parameters. But when you say the variational parameters, we are talking about a lot of differential, it's like it's a vector, you know, which is the gradient of the first variational parameter, the gradient of the second variational parameter, 2. So for computing some gradients, for some variational parameters, you can use one method. For computing the gradients of another variational parameter, you can use another method. I mean, eventually you could do it. But the nice thing is like people is getting kind of approximated way to do a reparameterization trick in something which is close to a categorical variable. I mean, there is a very active area of research trying to fix this issue. Perfect, yes. I think if you look at this paper, you will find some nice references. Yeah. Yes. Sure, man. I mean, there are quite a lot. Yeah. I mean, the question is sometimes is, I mean, once you have that, you can create new distribution which are made of you sample from some distribution and then you transform the distribution to some function and then you have another. Once you have some distribution which is reparameterizable, then you transform the sample of the distribution through an invertible function, you end up having a different distribution. And this distribution, if the first one is reparameterizable, you know, all the whole process is going to be reparameterizable as well. I mean, you will learn that a lot in the normalizing flows, okay? You will see how you can really go far beyond the conjugate exponential family. Yeah. More questions? Yes. I think it's a really, 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 really nice, very nice question. So usually one, because the variance is very small. Yeah. Usually one is enough. Yeah. I mean, again, I'm sure that someone can tell me, okay, here is an example of an approximation with the reparametrization trick, with one sample, one Monte Carlo sample, then you fail. Sure. But there are many cases where even one sample is enough. Okay. Yeah. I mean, when you mean cannot be reparameterized. Exactly. So, I mean, well, the beta can be reparameterized. Okay, perfect. So this is like just an example. Okay, the beta can be reparameterized. But anyway, if you cannot reparameterize it, this is not possible. Then you can't use the reparameterization trick, but you can use the score function gradient. Okay, but then you will have to sample a lot. Okay, yeah, you will have to sample a lot. I mean, yes, I mean, but the only reason because it's more efficient is just, well, I mean, there can be some minor change, but the main reason because it's more efficient, like you need less samples, okay, to achieve the kind of the level of variance that allows you to really move towards your solution. Yeah. Okay, I think we can continue, but let me see. Here we are. Next thing, okay. So we want you to convince yourself. Perfect. So what we are going to ask you here is just, we are going to go back to the previous exercise, the same model, the linear regression model that we had before, the one that you computed the score function gradient, okay? And now we will ask you just, it's like we provide all the information, all the gradients that need to be, needs to be coded in order to implement this reparametrization trick, and then you really observe how it's behaved. Let me go to okay, I don't know. So first question, just maybe you are not aware of that, but here is like, you have this stuff over here, okay? And then you click here, and then you have all the table of contents, and you can really jump through the different section. And, maybe you are not aware, I don't know, I probably yes, but just in case, it's like, if you introduce a change in the notebook, you can save this notebook to your Google Drive account, so you can take over later, okay? Just a small reminder, but the question is, here we have, okay, let me see. This is the reparameterization gradient. This is the equation for reparameterization gradient. And then you have here all the derivation to implement that, okay? Are all the details that we need to implement that, okay? And then you need this gradient, and also this gradient. So we give you all the detail. Perfect, all the gradients. And then all these gradients are implemented here. Perfect. Okay, all this is implemented here. So you don't really have to code anything. The only thing that we ask you to do is, well, have a look, of course, try to convince yourself. Okay, but the main point of this exercise is, is to compute the gradients and look at these plots, okay, and then compare with the score function gradient, change the number of Monte Carlo samples and see that really the variance, is much more stable, the convergence, okay, of this approach than it was before. Perfect. So how many times do we have? Yeah. And then I'm going to upload right now the solution of this notebook. So if you didn't have the opportunity or the time to really code the missing part of the score gradient function, I will upload right now the solution. So in just 1 minute, you can click on the link that is in the GitHub repo, and then you will have access directly to this solution black box inference notebook. Okay. Okay. Hi, everybody. So we have to continue. Okay. I hope you have the time to look at all of this. So let me make, so some clarifications. Okay. So before this exercise, I kind of give you high level intuition. Okay. Let's try now to be a bit deeper. Okay. Just a bit deeper. Okay. And then we will go through the solution. So first thing, why do we need a small number of samples? So that's true that the reparametrization trick provides less variance. But the nice thing, is like, at least because we are doing optimization. Okay, so we are optimizing a function. The main thing that an optimizer needs is the gradient. Perfect. Okay, and the nice thing here is you realize is like, before that, if you choose only a single sample, you may end up pointing in the completely wrong direction. Perfect. But the nice thing about the reparametrization trick is like, most of the cases, let me see, most of the cases, every sample, every Monte Carlo sample that you use, okay, is kind of pointing towards the mouth of the posterior. Okay, this is what you can see in this image over here. Okay, where is this? This is another reason, because it's enough to have a much smaller number of samples. Perfect. Yes. More things. So the idea is like, as you saw before, let me see. So when you run this notebook, the main point is, when we have a very picky posterior, then the log Q term of the reparametrization gradient, the gradient of the log Q term is really to dominate a bit. Okay. This is because the gradients are not at this point really pointing to the mouth of the posterior, because when it's very peaky, then the gradient is a bit larger. Okay. And then you see the log Q term of the reparametrization trick make the gradient pointing not really towards the mouth of the posterior, but as we are getting there, then the gradients start to be really pointing much more toward the posterior. Okay, but the main thing here is like, we don't really see this kind of jumping around that we observed, okay, in the score gradient, estimator, okay, in the score function estimator. What we see here is a much more stable behavior of the convergence of this method. And the nice thing here is like, when you plot the evolution of the elbow at the very end, this is what we see. So because we are kind of consistently pointing towards the maximum of the elbow, okay, we can see that along the convergence, the optimization process, we are kind of consistently improving the estimation for the, the orange line, which is the reparameterization trick or the reparameterization function method. Okay, and for the blue line, we can see these jumps in the elbow, which means that sometimes we are optimizing, sometimes we take the wrong step and then we minimize, sometimes we optimize, sometimes we, it's much more noisy. If we zoom in the last part, okay, this is what we get, and then we can really see this kind of much more noisy, much larger, okay, sorry, much variance in the evolution of the elbow. It's just because sometimes, you point in the right direction, then you improve, sometimes you point in the wrong direction, then you minimize it, Okay, it's not as stable as is the case of the kind of gradients that you estimate using this reparametrization trick. Perfect. Any other question? Any questions? Clarification? Yes. No, not at all. Not at all. Okay, not at all. This is completely independent, but of course it may have. I mean, the question is like usually. I mean, let me see. So if you have 100 parameters, your model have 100 parameters, okay? Or let's say like 1,000 parameters to make it easy, okay? So your elbow function, okay? So how many parameters does it have? Let's think about that. I have 1,000 parameters. It means that if I go for a mean field, I will place 1,000 normal distributions, okay? Each normal distribution requires how many lambda, how many variational parameters? 2. 1,000 normal distribution, one for each of my parameters, means that I will have, my elbow function will have 2,000 parameters. Then I will have to optimize a function which is defined by 2,000 parameters. If I go generalize mean field, you know, I say, okay, I want to place a multivariate Gaussian over the 1,000 parameters. Okay. So how many parameters do I need to parameterize this multivariate Gaussian? 1,000 for the mean, 1,000,000 for the covariance matrix, and maybe smaller. You know. Then the elbow function will have much larger number of parameters to optimize, okay? So, you know, you may have a nice optimizer, but you know, when you increase the number of parameters, I mean, there is a problem. And also there is problems about numerical stability because they have, you have to invert the matrix. I mean, there is a lot of things going on there, but this is the kind of general idea. There is always a payoff to go beyond the mean field, okay? Yeah. More questions? Yes. Exactly. Yes. So say again, say again. I mean, then you have, I mean, let me see. Let me see. Let me see. This is a good question. Yeah. Let me see. Yes. The question is here is like, you have two unbiased estimates, okay? So we need a Monte Carlo approximation to estimate the gradient, okay? But we never compute, I mean, let me see. So that would be the gradient of the log of the probability of the data, given theta plus the log of the probability of theta when you factorize that, okay? But this guy, okay, when you expand this, the log of this guy, then you have one term for each data point, okay? So at the end, you don't really compute all these terms for all the data points, but you take a mini batch, okay? And then you get again an unbiased estimation. So you add two unbiased estimation one over another, and then you increase the noise. So how much add each of these two things together? Which is the worst one, or which is the largest one, which introduce much more variance than the another? It's a hard question. Okay, I would say it's a hard question to answer because some people even say like this kind of variance that is introduced by the stochastic gradient descent is positive for generalization. Okay, so I think it's a complex question to answer. Yeah. Sorry about this. Yeah. Oh. Okay. Okay. Perfect. So I can say that we haven't prepared this question, okay, before that, because the answer is yes. This is an excellent question to move to my next slides, okay. So let's go back and make a recap, okay, and then I will take more questions if you have. This is a nice question. So the question is like, so far we have been asking you to make a lot of manual derivations. Do you think this is feasible? No. This is not feasible. It's not feasible at all. Okay. So I will tell you the nice thing, but let me recap, and then we move to this question. So reparameterization gradients, we have seen like they are nice. They are quite nice, mainly because they exploit the gradient of the model. Okay. Perfect. Problems. Requires the variational approximation to be reparameterizable, also requires these two guys to be differentiable. These are requirements that not always fulfill, okay? A score function, doesn't work so well. Perfect. But the nice thing is like has, not so strong requirements, only requires this guy to be differentiable, and the only thing for this guy is to be computable, okay, which is a not so strong requirement, okay. But even though you may find models where this guy is not computable, okay, but this is not something that we will discuss here. Anyway, takeaway message, okay. If you can do reparameterization trick, go with it, okay. If your model, your variational approximation fulfill these requirements, go with it, okay? If not, try this guy. It may work, okay? May work. Usually this guy works quite well, and this guy depends on the specific problem setting that you have. Perfect, yes. So let's go back to the kind of general receipt. Okay, sorry. Let's go back to the kind of I'm going to be quicker. Okay, sorry. Let's go back to the general receipt that we have thanks to this black box variational inference. So the first thing that we have to do, which is a kind of manual task, is to define our model, okay, with our prior. Second thing, it's a kind of manual task, even though we'll show you how we can even try to make it automatic right now, is to define the variational distribution. Then we have to optimize the elbow. Nicely, the elbow can be optimized using one of these optimization methods like stochastic gradient descent, Adam, all these optimizers that we have nowadays, okay, in any of these toolbox. And for optimizing this guy, we have to compute the gradient of the elbow, and then we have the score function of the reparameterization gradient, which is the nice thing. And then that answers your question. It's like for computing this score function or even the reparameterization gradient, that involves computing the gradient of some function with respect to theta, with respect to lambda. And, when we build on top of these PPLs that builds on top of these deep learning frameworks, we have something which is called automatic differentiation engines. So it means that we don't have to compute the gradients. The functionality provided by the underlying computation engine compute the gradients for free for us, okay? So this is a completely automatic task. The only really manual task is to define our model and our prior. Perfect. And then automatically we will run anti-convergence, and then we will find an approximation over posterior. Perfect. And then, we will show you now how all of this is coded within Pyro. Okay? Yeah.
Okay, so time flies when you have fun. We have around half an hour before we have a break, a coffee break. So we are going to do a bit of improvisation, also meaning that we don't quite follow the plan that we originally set up. It also means that some of the notebooks that are made available to you will not be covered quite the same detail as we had laid out. But what we want to address now is to link all the theoretical foundations that we've been through until now to Pyro, and see, also addressing the comment that we just had, to see how we can automate the overall process, both in terms of model specification and doing the inference part. So again, I think we have already covered this quite a lot. We have our Pyro modeling scheme. We have already said a lot about modeling, and we've talked about model criticisms in terms of the box loop and so forth. And what we have mostly dwelled around today is the inference part, where we have been focusing on the variational aspect, but actually Pyro is also much broader, also supporting not only variational inference, but also Monte Carlo estimation for doing inference instead of just the variational components. And again, here we would also like to point out that although we have used Pyro as our running example or framework for doing the examples, then it's just one example that we have chosen for pedagogical reasons. There are many other languages that you could use, for instance, TensorFlow probability and NumPy, which is a local alternative, and so forth. So jumping straight to it, so we have, yesterday you saw our running example with a very simple Pyro model, where we had a temperature variable and we had a sensor variable, and they were sort of giving these two distributions up here, which in combination defined a joint distribution over our domain, where we could calculate the probability of the sensor variable and the temperature. And when we ventured into Pyro, then we had the Pyro sample construct that mimics what we would refer to as random variables. And we could also assign observations to these random variables using the ops argument or ops keyword. So our models took the form that we have here. In this case here, we specified with the dictionary the data that we had available. We had a model specification given by a function, given by this function here, and we have our two sample statements corresponding to our two variables up here. And for the latter part, we include the data on the sensor that we actually make observations. So that was for our model. What we actually want to do is to do inference. And that would mean that we would like to calculate, say, the posterior distribution over the temperature given an observation over the sensor. And here we resort to the variational solutions, minimizing the Kullback-Leibler divergence between our variational distribution and our true posterior distribution, and doing that using the formulations that we've covered so far by transforming it into an optimization problem where we are optimizing the evidence lower bound instead. And all this process here is supported by Pyro using Pyro guides. So Pyro guides are basically specifications of the Q distributions, so the variational distributions that we use in our variational settings. This is something that we made hidden in the notebooks that you saw yesterday, and this is what we will try to expand a bit on here today, so you can get a bit of flavor for what you can actually do with the guides and how you can work with them. So these Q distributions here in Pyro are not just limited to the variational distributions or doing variational inference. They can also be used for doing other types of inference that we haven't covered, importance sampling, MCMC, and so forth. So that would be going back to Antonio's lecture the other day. So a bit more formally, so in Pyro, the guides are, again, arbitrary stochastic functions, and they are required to produce samples for those variables in the model that are not observed. So for our model before, that would then be our temperature variable that we didn't observe, but not the sensor variable because we assumed evidence on that variable. The requirements for specifying the guide is that the guide should have the same signature as the model specification. So in the model that we have here, so that's the same model specification we saw on the previous slide, the model take a bunch of observations in through the parameter ops here, and that ops should also appear in the guide that we have down here. In addition, we should also have that all the unobserved sample statements that appear in the model, they should also appear in the guide. Up here, we only have one unobserved sample statement, that's for the temperature variable, and that should also appear down here in the guide. Now, for specifying the guide, which corresponds to our variational distribution, we also need to specify our variational parameters. And that is being done using the statement pyro.param. So here we are constructing a parameter in Pyro, which again corresponds to one of our variational parameters. In this case here, we are giving it a name mean, and we are giving it an initialization value. In this case here, we are setting it to 0. And we have another parameter b here, which corresponds to a scale, which is given an initialization value of 1. And then we also put in the constraint that this parameter here should always be positive, because it corresponds to the standard deviation of our variational distribution that we have down here, which in this case here is defined as a normal distribution. So the two variational parameters, a and b here, plays the role of the mean and the standard deviation of our variational distribution. And that's basically all there is to it when you specify guides using Pyro or variational distributions using Pyro. You need to make sure that the signatures match up for the model and the guide, and that all unobserved sample statements in the model also appear in the guide using the same name. So here you can see we have the naming convention of having the temperature variable also called temp here, and that should also be the same name that is being used in the guide. Yes. Question? Yes. Sorry, it's... Yeah. That's our, yeah, exactly. So this part down here would correspond to our variational posterior distribution over the temperature variable. Exactly. Other questions for this part? Yeah. No, it actually matters, because that would be the starting point for your optimization procedure that is going to run underneath. Okay. Yeah. Yes. Exactly. Yes. So then in that case, you would be defining a variational distribution that would correspond to a normal distribution with a mean of 0 and then a variational parameter for the standard deviation. Yes. Yep. Okay, so let's take a slightly more elaborate example. So we have here a simple Gaussian model that you have already seen before. So the model specification here is actually the same as the model specification that you played around with before lunch. On top it says exercise, but again, time flies. So instead of having an exercise here, we will actually have a solution walkthrough. So our setup here is that we are generating a bunch of data points from a normal distribution with a mean mu and a precision gamma. Mu and gamma are assumed to be unknown, so we are giving them prior distributions. Mu has a prior distribution that is normally distributed with a mean of 0 and a variance of tau, and gamma, the precision, is given a gamma distribution. And what we do when we start to set this here up in Pyro, the first thing you should specify, in addition to all the other packages that are being imported, you should use pyro-infer and then import SVI, which is sort of a wrapper for the stochastic variational inference framework that we have been discussing earlier. And then trace elbow here, which is a specification of our loss function. So you can simply, would be the elbow function that we are trying to optimize. Then what we have here is that we are generating some data points. So we're generating 100 data points. We have with normal distribution where we know the mean is 5 and the precision here is 1. This is what's happening here. Then we have our model specification. We have gamma and mu, the parameters for our normal distribution that were assumed to be random variables, unknown parameters. That's why we use the sample statements here. We give them the names corresponding to the variable names here. And we initialized gamma again with the gamma distribution and mu with the normal distribution. And then we use pyro plate to iterate over our data points. And we have for each data point, we have a variable x with the corresponding mu and scale that we've specified up here. So the scale being the square root of the square root of 1 over gamma, which corresponds to the variance 1 over gamma. And then we assign that the data that we are given as input. For the guide, we have the requirements that the signature should be the same. So we have data up here, and then we just assign data equals none here. And then we should have a variable for each of the unobserved variables. We have gamma and mu being unobserved. They appear here, pyrosample gamma, pyrosample mu. Both of them are assumed to, the first gamma is assumed to have a gamma distribution as the posterior, corresponding to the same or coming from the same distribution family as the prior. Mu is assumed to have a normal distribution. Both of them are parameterized by 2 parameters, which we treat as unknown variational parameters that we want to optimize. Alpha Q and alpha beta is defined here with the corresponding names. Both of them are constrained to be positive. And we have mu and the scale down here, where the scale is also assumed to be positive. And that's basically all we need to do in order to set up our guide specification that we have here. Then we can start to do learning. And this here is basically the learning setup that we had hidden for you during the lecture that we had yesterday. Yes, we have a question. Good questions. I don't have an overview of that. So there you would need to consult the Pyro documentation. Yeah. Very careful. They have to match 1-to-1. So no, you need to make sure that when you, for instance, have gamma and mu up here, they need to appear under the same names down here, because that's how Pyro under the hood tries to match up the variables and during the optimization process. Yeah. Yes. Yeah. No, you could actually here, you could probably drop the equal none here and then it would still work. But it doesn't use the data provided to the guide. In this case here, it's simply because that it's required by Pyro that the signatures should be the same for the model and the guide. Yeah. Yes, so you could, so we don't have any constraints on what kind of code that you could put in here. So you could make your own transformations of the parameters, soft plus, for instance, and then you would be one way to avoid these, the use of the constraints that we have here. Yes. Okay. So the code that we have here is what handles the optimization. And again, as I mentioned, that's basically the same code that we had hidden for you from you yesterday. So we specify a learning rate here. We use the Atom optimizer for doing the optimization. We call this function here clear parameter store. So that means that all the variational parameters are just being reinitialized. We call our stochastic, make an instance call to our stochastic variational inference that should be given both the model, the guide, the optimizer, and the loss function that we are trying to minimize. And here we are minimizing a loss which would correspond to the negative of the which corresponds to the negative of the elbow. In effect, that means that we are maximizing the elbow. And then we are doing iterations here. So now we are iterating for 3,000 iterations. SVI.step means that we are taking one gradient step. And here we are keeping track of the loss that we are calculating. So this gradient step here is also returning a loss. And then we are simply iterating for 3,000 iterations. And when we do that, we can see how the loss generally decreases here. And if we plot that, we can get access to the parameters that we were trying, to the variational parameters that we were optimizing over. And again, they are part or included in the Pyro parameter store. That's the naming convention. And you can get access to them using Pyro param and then the name of the variable that you are, or the parameter that you're trying to access. And when you do learning, these are sort of the values that you end up finding. So we started up with a mean of 5, and we can see that we actually, our posterior distribution have the same value here. And we have also sort of an alpha and a beta where the ratio is more or less around 1. So we are also in the same, the mean of the gamma distribution would correspond roughly to the precision that we started out with. And we have here sort of a plot of the elbow, and just to keep it brief, what you can see here is that we have some kind of convergence, but we also have a lot of small spikes here and there. So that also means that since we are doing the stochastic variational inference, we don't have this nice non-decreasing evolution of the elbow as we saw earlier today. But this was also what Andrés and Helge mentioned when we saw the plots about using the score function and the repronotarization trick. So that is basically it. What we have planned to do, we don't have time for, so we will do another thing. We will give you the option of using the last 13 minutes before the break to take a look at 2 different notebooks. You can pick your what you would like. The first one here is on Bayesian linear regression. That basically tries to go through the setup that you've seen several times by now, but now doing Bayesian linear regression using Pyro. We are using both different types of guides in here. You can play around with it. Maybe you can even customize your own guide. There has been several references to generalized mean fields. So for those of you who are interested, you can go through, take a look at the specification here, go down to the guide specifications. We have an example of a manually specified guide. Maybe you can try to experiment adapting to that so that you get a generalized mean field rather than just a standard mean field. We also have another notebook that you can play around with. And here you can really be adventurous because we also have a Bayesian logistic regression problem for you. So we are moving away from the purely linear regression. And here there's also the code available. Here you will also find a small exercise for actually extending the model that is given here in the model specification. Down here. So you've been asked to complete the model here, and you can also try to, if time permits, spend a few minutes on playing around with the guide to get a feel for how the guide is being specified in Pyro. There's unfortunately not that much time for doing this, but I we still hope that you can sort of spend the remaining 10, 11 minutes and get a bit of feel for this, and then there'll be a coffee break afterwards. Sorry? Yeah, the solutions for these exercises here will also be made available, obviously. Yes.